Hello and a warm welcome to our talk, Wearable Decubitus Prophylaxis tool based on machine learning methods. We want to introduce the early findings of our project called Kiprode. The project name Kiprode origins from the German name KI Prophylaxis for decubitus. But let's start with my background first. My name is Lawrence Grünabel and I'm working as a project manager, team lead and system engineer at Fraunhofer for 4 years now.
Also a warm welcome from my side.
The presentation will start with a short intro of Fraunhofer and why we work on wound prophylaxis. After that, I will introduce our system hardware to research on wound occurrence. My colleague Ferdinand Heinrich will present the developed data analysis methods and how we plan to find early detection means of wound emergence with machine learning methods. So before starting with the technical presentation, I will shortly introduce Fraunhofer. The Fraunhofer MFT is part of the Fraunhofer organization that is the leading institution in applied research in Europe. The research spans several fields of science or economics and includes a lot of international collaborations. The aim is to bring state-of-the-art research close to the industry. Therefore, Fraunhofer currently employs around 29,000 people at 74 research institutes. One of them is the EMFT, which is the abbreviation for Institution for Microsystems and Solid-State Technologies in German. It combines research on sensors and actuators in certain fields, such as microdosing, printed sensors, and its manufacturing technologies. In recent years, the field of artificial intelligence and machine learning algorithms are growing in importance. Besides projects aiming at increasing lifetime and predicting failures of processing equipment, a strong focus is on digitizing medical technology. Innovative sensor solutions are implemented, for example, to detect harmful bacteria or diagnose and forecast different types of disease. The difficult task of wound prophylaxis is addressed by a competent consortium of 3 further partners besides Fraunhofer. Monks takes care of data privacy and safe data transfer to allow analysis of medical data. They are a certified and established company in the field of telemedicine in Germany and are currently enlarging their field of operation. The medical expertise within the project is provided by the clinic of the TU Munich and the Bavarian Food Network. The Bavarian Food Network is a network of physicians, caretakers and other partners involved in wound therapy, particularly diabetics and diabetic foot ulcers. On the other side, the MRI is a partner from the clinical side that treat a lot of patients with decubitus wounds. Both medical partners know the painful and long-lasting therapy of severe wounds and have a high motivation to work on early detection means. I will start the technical talk with the medical need for our project. The underlying problem that this project addresses is a lot of avoidable stress and pain for patients. Many diabetics suffer from the diabetic foot syndrome. Due to the consequences of the disease, the blood circulation is limited, especially in the legs and feet. The nerves may degrade additionally, which leads to a loss of sensation and hence any detection of unpleasant events may completely disappear. Both symptoms together often lead to harmful wounds that are detected in very late stages only. The worst case is an amputation to hinder consecutive blood poisoning. This happens around 40,000 times in Germany every year. The cost for sufferers and the healthcare system is tremendous. Very similar, but still different, is the occurrence of decubity, also called bed sore. Risk patients with certain pre-existing conditions may develop wounds due to an overdose of pressure load on a certain risk location of their body. The result is a stressful surgery and a long-lasting therapy. In Germany, we have more than 400,000 severe wounds or decubitus ulcers annually. Due to leading experts, many of these wounds could be avoided by early prediction measures. This project aims at developing a system to detect wound occurrences in very early stages and hence completely avoid them. The hypothesis bases on the assumption that wound emergence is detectable at the skin far before it usually attracts attention. This might be due to bad blood and nutrition delivery that can be detected via vital sign monitoring. Since a lot of data is generated during monitoring, the way of analysis is searching for critical parameters by means of machine learning algorithms. The sensor data is combined with medical expertise of the Technical University Munich and the FootNet Bavaria. Physicians or nursing staff add their diagnosis into a specially developed app where all patient data is collected and combined with the sensor output. The data is transmitted via secure connections to an approved database and then used for intelligent data analysis. The data analysis bases on the main hypothesis that I want to introduce here. Long-term pressure load leads to stress for the skin. A healthy subject gets alarmed by the nervous system if it's getting too much stress, and the subject can relocate the pressure load. However, a preconditioned patient does not necessarily get this alarm, and the skin can become seriously damaged. In early stages, the perfusion is hindered to a degree that oxygen saturation and skin temperature are expected to decrease at a risk area. If actually a wound occurs, the temperature can rise again due to infections. Our machine learning algorithms shall find these patterns within vital sign measurements and warn the patient in time. Because of medical relevance and technical availability, certain vital parameters are selected for continuous observation. Those include the oxygen saturation in blood vessels close to the skin surface to determine the quality of blood supply at a certain location. Another important factor, therefore, is the skin temperature, whereas strong variations in heart rate may suggest a general health issue. Within the planned study with around 100 participants, we want to find a correlation between those parameters and the occurrence of pressure wounds to derive critical predictors for early identification in the future. With a super thin pressure sensor foil, we want to observe the pressure load on the risk locations and derive a measure when the pressure exceeds a critical level. Our partner physicians provide the medical supervision to evaluate the results correctly. Currently, the estimation of the risk of an emerging pressure ulcer is happening very subjective, since it's optically estimated by medical experts. For ambulant patients, this means that a control usually takes place irregularly when a nursing service comes by or when they visit a doctor. Continuous observation is not possible. Since ulcers are wounds that are emerging rapidly in case of a damageable event, this can be too late. For testing blood circulation at certain risk areas, a medical expert pushes into the skin and observes its behavior. Hence, current methods of early wound detection rely on subjective estimation without comparable quality. Also, continuous monitoring is not possible for ambulant patients. After the medical need of our project has been described, I want to introduce our developed hardware system. The schematic shows a representation of our sensor system. The developed prototype of a medical wearable reads the sensors regularly and stores data for later analysis. Future developments can easily integrate the technology in a handy medical device. As depicted in the schematic, a thin pressure sensor foil is attached at a risk area of a patient's skin where wounds show a high risk of emergence. Close to that, but with little pressure load, the vital signs are measured. Local proximity is important because local skin modifications should be detected. The system comprises several sensors, such as the reflective pulse oximetry. A LED emits light into the skin and measures the reflection that depends on blood flow. Vital signs can be extracted from the response signal. An integration into a pressure node, as used in this project, is displayed on the right. Furthermore, it includes the previously mentioned pressure sensor foil, which is displayed below. Due to its feet-like form, it can be integrated into a shoe and worn all day. In a follow-up project, it should be connected to a smartphone or similar device to give an alarm in case of emergency. Here we focus on generating the hardware and software infrastructure to get the critical predictors and not the communication. The graph on the lower right shows a raw signal of the pulse oximeter that clearly allows to determine the heart rate and blood oxygenation saturation. The extracted values are displayed within the next graph and plotted over a complete night. Expected SpO2 or blood oxygenation values of a healthy subject lie above 95%, as seen here. The red line constitutes valid measurements where only a few failed. This is an important parameter for later data analysis. The introduced prototype of a medical wearable for our studies is displayed here. All electronics is housed and marked with yellow. The small sensor node is marked in green and the super thin pressure sensor foil in red. The pressure sensor foil exists in two variants, in the feet-like form for preventing foot ulcers and in the rectangular form for decubitus prophylaxis. During studies, the two sensor variants are placed at subjects. The group with the risk of food ulcer emergence gets a sensor system installed at their feet with the pressure, foil and a shoe. Skin perfusion is monitored right across the foot since no place is available directly in the shoe. The other group of patients is bound to bed and bears the high risk of wound occurrence in the trochanter region and hence gets the sensor system there.
The generation of the dataset is an important part in machine learning, so we designed a data pipeline to transform the raw data to the machine learning ready dataset. Our first hardware version stores the raw data on an SD card. This raw data is sensitive data because it is personal medical data. In a clinical study, this data needs to be transferred from the hospital to the Fraunhofer Research Institute. This service is provided by the telemedicine data server Pflegekonsil. It holds proven certificate of secure data transfer and was designed by our partner Monks. We at the Fraunhofer Research Institute only store the anonymized data. Next, the data has to be pre-processed. This includes several steps. The data of every test person is aggregated. After cleaning up missing time steps and out-of-range sensor data, the missing sensor values are forward-filled up to a maximum of 5 time steps, which is the equivalent of 5 minutes. Then the data is split into relevant sections. The relevance of a section is defined by the proportion of usable sensor values. As the data representation, the ESCA-timed data format was chosen to make the dataset compatible with Python machine learning models. For the machine learning model presented in this work, the sensor values are filtered to represent the plausible physiological change rates.
Before going into detail about data analysis, I want to introduce how we generated our available data. The presented feasibility study comprises the verification of our developed prototype with a healthy subject with the goal for future use in clinical studies. The subject has worn our system of the decubitus prophylaxis variant during 17 nights with continuous monitoring of the introduced parameters. Recorded data is analyzed in the following. The first evaluation shows the vital sign trends over an exemplary night of the test subject. One can see the skin temperature at the top. The rise at the beginning probably arises from getting to bed and warming it. During the rest of the night, the temperature remains quite constant, with a few small variations that probably arise from different pressure onto the sensor. Examining the SpO2 value reveals a stable trend above 98%, which is in the expected range for a healthy subject. Only in critical situations it would fall significantly. The heart rate varies a lot during night and probably depends more on dreaming and sleep phases than on the actual health condition. Long-term observation is necessary here. The last graph depicts the normalized sum of all pressure elements that clearly show the time where the subject lies on the respective side. The red line indications arise from pattern recognition methods and are explained later. The heat map allows to determine areas of the pressure sensor foil and hence the respective skin area where most pressure occurs, here in the upper left corner. Those indicate risk areas for a preconditioned subject.
Now we have reached the machine learning part. This study uses data of a healthy test person, so we will not find a temporal sequence in the vital data that indicates the risk of a pressure injury. Therefore, the goal is to understand the interactions between the vital data. Technically, this can be achieved by clustering sequences of same temporal evolution. The method presented here is based on the matrix profile. The matrix profile is a method that stores the location and distance of every subsequence and its nearest neighbor. In this case, the distance or likeness is defined as the z-normalized Euclidean distance. In the picture, one use case of the matrix profile is shown. The most similar subsequences of the gray time series, the so-called motifs, are exactly defined by the matrix profile and are highlighted in red. As our data is composed of skin temperature, heart rate, oxygen jet saturation, and the sum of pressure, we need to find similar subsequences in 4-dimensional data. Luckily, the matrix profile can be used to find multidimensional motifs. In this picture, these motifs are again highlighted in red. But one problem with the multidimensional data is that an irrelevant time series depicted here in blue can shadow the location of the motifs. As can be seen in the lower screen matrix profile, P3, the minimum does not correspond with the starting location of the motifs. So, either one uses a matrix profile that only takes the two most common of the three dimensions into account, or alternatively, it is assured that irrelevant data is not included. Now, let's have a look at the clustering algorithm. First, the motif pairs that are more similar than a defined maximum distance are located. These subsequent pairs are the potential root of a cluster. In a second step, all nearest neighbors up to the maximum distance of each motif pair are located and counted. Then the biggest cluster is chosen. As a last step, the matrix profile is annotated to ignore already selected regions. This process is repeated until the desired number of clusters is calculated. One drawback of this implementation is that it's not as scalable as the standard matrix profile because of the nested calculation of the nearest neighbors. We implemented this algorithm in Python based on the StumpY library.
Next, we want to show the results of our clustering algorithms that depict the data analysis.
Shown here is the concatenated test person data of the 17 nights. The top graph shows the skin temperature, then follows the oxygen saturation, the heart rate, and the sum of pressure. Although this data is only from one test person, it already becomes apparent how difficult it is to analyze this data by visual inspection. We decided to search for clusters of subsequences with a length of 30 minutes, because we believe this is the time a physiological change might take. Furthermore, it was decided that the heart rate is not relevant for the clustering because it can be influenced by many indirect causes, like the sleeping phase. The resulting 3 clusters are highlighted in color. The unifying temporal evolution of each cluster is more apparent when looking at the clustered Z-normalized subsequences. In this figure, the orange and blue lines are the cluster roots, which are a motif pair, and the gray lines are the nearest neighbors. The first cluster shows a rise in skin temperature and SpO2 when the sensor recognizes a rise of the pressure load. This might be the standard response of the vital signs when the sleeping test person applies pressure to the area where the sensors are located. The second and third cluster both show a decrease of the sum of pressure, so the test person rolled off the pressure patch. Interestingly, both clusters show a decrease in skin temperature, but one cluster shows an increase in SpO2, while the other shows a decrease. The interpretation of such interactions is the task for medical domain experts. But our clustering algorithm helps to find and visualize potentially relevant interactions.
The last part of our presentation is the conclusion and how we plan to move ahead. The presented prototype of a medical wearable allows the continuous monitoring of pressure load and vital signs at risk areas of preconditioned patients. We could verify proper system functionality with a healthy subject without any negative impact on the skin, which is an important prerequisite for the project. Our developed algorithms allow to cluster recorded data and find multivariate patterns across several sensor gems. The analysis tool is ready to work with patient data and find the required prophylaxis parameters. We can start a clinical study with our system and generate important data to determine early prediction means. The following provides an overview of the used literature and the links to our partners that were introduced at the beginning of the presentation. Now we're coming to the end of our presentation. I hope you could learn about wound prophylaxis, and I want to thank you for your attention. I would also give a special thanks to the federal government of Germany that allows us to research on this important matter. If you're interested in this topic, or you got some questions, or you're even thinking about a possible collaboration in this field, feel free to contact us via email or in the intended question slot. Thank you.